we've been looking at Z transform properties, and we looked at the very first property, namely linearity. We will now look at the next one, and this is the delay property. So, we have x of n having Z transform x of z, and in general its ROC is of the form R1 less than mod z less than R2. We want to see how the Z transform of a related sequence, namely x of n minus n naught, is related to the original sequence's Z transform, and the property is z to the minus n naught times x of z, and the ROC is same except possibly for the addition or deletion of 0 and or infinity. And the intuition behind this is, if you have a causal sequence and then if you delay it by some samples to the left, so that you have now samples corresponding to negative indices, then in the earlier case 0 is not part of the ROC, but infinity is. If you make it non-causal, then infinity gets eliminated from the ROC, and the corresponding DTFT property is this. All you need to do is you need to replace z by e to the j omega. Therefore, this becomes e to the minus j omega n naught times x of e to the j omega. And as a simple application of this, remember when we are looking at the linearity property, we had given this as one of the sequences, and we had mentioned that the transform of this was this. You can of course very easily get this from first principles, but using the delay property this becomes really easy. By the way, the proof of the delay property is just almost one line. So, if y of n is x of n minus n naught, the Z transform of the shifted sequence is this, and then all you need to do is put n minus n naught equals L, and immediately this simplifies to this. Just one line proof. And to derive the transform of this, you can write this as a to the cap n, a to the n minus n, u of n minus n. So, nothing has changed. So, this you can think of this as x of n minus n, where x of n is a to the n u of n, and hence you are able to see that this is nothing but a to the n, and x of n minus cap n has z transform z to the minus n times x of z. X of z of course is 1 by 1 minus a z inverse. So, the delay property helps you get this transform immediately. Another example, suppose if you had h of n to be 1 between minus cap n to plus cap n, h of z of course is and this can be written as a times 1 minus r power n by 1 minus r, and this is nothing but z to the n minus z to the n minus 1 by one minus z inverse. And if you had g of n, which is h of n minus cap n, this of course is 1 now for 0 less than or equal to little n less than or equal to 2 times n. All we have done is we have shifted this non-causal sequence by cap n sample, so that it now begins at little n equal to 0. And g of z is, all you need to do is you need to multiply the previous transform by z to the minus n. Therefore, this is nothing but this. We can also look at the corresponding Fourier transforms. So, this is nothing but h of z evaluated at z equal to e to the j omega. You can do this because this after all is a finite duration sequence, and the ROC does indeed contain the unit circle, because the ROC is the entire z plane except 0 and infinity. And for this particular example, you can write the given h of z is this. Let me multiply the numerator and the denominator by z power half. So, this becomes n plus half, and this becomes this, and denominator if you multiply by z power half, this becomes z power half minus z power minus half. And the reason for doing this is we want the DTFT of the given sequence. Therefore, now if you replace z by e to the j omega, this becomes e to the j omega n plus half minus e to the minus j omega n plus half by e to the j omega by 2 minus e to the minus j omega by 2, and this is nothing but sine n plus half omega by sine omega by 2, and this is also commonly written as sine 2n plus 1 omega by 2 by sine omega by 2. And this function sine n omega by 2 by sine omega by 2, this is called as the Dirichlet kernel. And MATLAB you can look up the command Diric, D-I-R-I-C, that evaluates this function, and suppose I set z to be linspace generates points between a comma b, and you can specify the number of points you want between a and b. So, this is this, and then you can plot z which is 0 to 4 pi, and I am plotting Diric of z comma 7. So, here cap n is 7. So, this is what this function is. And clearly this function is the Fourier transform of a sequence, and this is 2 pi periodic. So, here I have plotted from 0 to 4 pi. So, that is why you see 2 periods here. So, what is happening at 0 gets repeated at 2 pi, and in MATLAB if you say axis tight, it will plot the axis just limiting itself to the data range. So, this is the Dirichlet kernel. So, this is sine n omega by 2 by sine omega by 2. In continuous time Fourier transform, you have come across the sinc function sine pi t by pi t, and later when we do sampling we will relate these two functions. So, from the delay property, it is easy to see that x of n minus 1 is nothing but z inverse x of z, and this property is used in block diagrams. Suppose you had x of n, and if the block diagram is labeled as z inverse, then this is a simple delay. Therefore, this y of n is nothing but x of n minus 1. Instead of z inverse, if you had z to the minus cap n, then the delay will be by cap n samples. So, if in block diagrams, if you see things like z inverse or z to the minus k and so on, then that stands for a delay by so many samples. And if in x of n minus n naught, if n naught were negative, then this advances the input rather than delaying it. So, n naught can either be positive or negative. Now, this delay property also can be used to point out one important consequence of systems described by linear constant coefficient difference equations. Therefore, suppose you had y of n like this, a k y of n minus k, similar to what was happening in the continuous time case, where you took a system with LCCDE, but in this case it is differential equations, then you transformed it using the Laplace transform. So, here we will do something similar. We will transform this into the z domain. This after all is the input output relationship. So, now if you transform it to the z domain, this becomes a k, y of n minus k is nothing but z to the minus k y of z, and this is k going from 0 to cap m b k z to the minus k x of z. Now, you can collect all terms involving y of z. So, this becomes 1 plus k going from 1 to cap n a k z to the minus k, and on this side we have x of z k going from 0 to cap m b k z to the minus k. And when I had introduced this difference equation, one of the questions raised was, why do you have a minus sign here, right? And the only reason why a minus sign is used is so that when you take it to the other side, this becomes plus. Otherwise, if this were a minus, you have to carry the minus sign throughout all the terms. That's the only reason. It's just a cosmetic notation. And this, of course, can be rewritten as y of z by x of z, and this is k going from 0 to cap m b k z to the minus k by 1 plus k going from 1 to cap n a k z to the minus k, and this is of the form b of z over a of z, and just as in the continuous time case where you called y of s over x of s as each of s, which was the system transfer function, here y of z by h of z is the discrete times system transfer function in the z domain. And the important consequence of this is now a rational transfer function. So, systems described by linear constant coefficient difference equations give rise to transfer functions that are rational, and you can actually work these steps backwards. Given a system with rational transfer function, there is always a corresponding LCCD associated with it in the time domain. Therefore, LCCD in the time domain gives rise to systems with rational transfer function. Systems with rational transfer functions have a corresponding time domain implementation that involves linear constant coefficient difference equations, which is the exact counterpart of LCCD in continuous time, where D stands for differential there, giving rise to systems with rational transfer function in the Laplace domain. So, now we are ready to answer the question as to why we are enamored by this class. This question has been raised more than once. The reason why this class is of so much importance to us is this is the only class that can be realized in practice. In continuous time case, if you had a system with rational transfer function h of s, which is of the form b of s over a of s, suppose the transfer function is something that you want, say for example it is a low pass filter, you need to actually realize this in practice, and any b of s over a of s can always be realized in practice using R, L and C. Given an RLC circuit, what you have been doing in that course is you would replace R by R, L by S times L and C by 1 by SC, and then you will write equations, and then you will be able to come up with the system transfer function. The converse also is true. Given an arbitrary transfer function of the form b of s over a of s, there exists an RLC realization of this. So, there is no use in having a nice transfer function that in terms of design does what you want it to do, but if you cannot realize it, this is absolutely useless. But if you did a course on network synthesis, you can always realize this in practice. Similarly, here given a rational transfer function in the z domain, it corresponds to a linear constant coefficient difference equation, and in terms of realization, all you need are multiplier coefficients and delay elements. Once you have multiplier coefficients and delay elements, you can realize this difference equation in practice. All right, and this is the reason why this class is so important. The other icing on the cake is it is not only just merely realizable, but it also gives rise to transfer functions that are extremely useful in practice. There is no point if this is realizable but does not produce too many useful transfer functions. It does provide a large variety of transfer functions that are extremely useful in practice and can also be realized. And somebody made a remark when I had talked about y of t equals x of t minus tau, right? I think you made the remark about this one. Now let us see the differences between this continuous time and discrete time. You had x of t, so this has transform x of s, and if you look at x of t minus tau, this is e to the minus s tau x of s. So, the delay element in continuous time, that transfer function is e to the minus s tau. On the other hand, if you had x of n, which is x of z, x of n minus n naught is z to the minus n naught times x of z. Here the delay element has transfer function z to the minus n naught. Okay, so if you compare these two, is there any point that kind of jumps out at you? Suppose your original system had, if this x of s were rational, what about this thing? Is it still rational or takes it out of that class? It is no longer a rational Laplace transform. Whereas here, if x of z were rational of the form p of z over q of z, this continues to be rational. All right. So, a delay element in discrete time, which is z to the minus n naught, is indeed a rational transfer function, whereas the corresponding counterpart in continuous time is not. So, this is very important to keep in mind, that the only class that can be realized in practice are the class of rational transfer functions. In continuous time, you realize them using R, L and C. In discrete time, for realization you need multiplier and delay elements. You can realize systems with rational transfer function. Now, continue with the delay property. Let us look at this for the DTFT. So, this was e to the minus j omega n naught times x of e to the j omega. One thing about the DTFT that is different from the Z transform is, the Z transform is a complex function of a complex variable. So, really you need 4 dimensions to plot it, so we cannot visualize it. On the other hand, the DTFT, the independent variable is omega, which is real valued quantity, and omega you need to let it vary only from 0 to 2 pi or between minus pi and pi, because this is periodic. Therefore, the DTFT is a complex function of a real variable. Therefore, you can actually plot it in 3D. You need 1 dimension for omega for the independent variable and 2 dimensions for the dependent variable, real part and imaginary part. Typically, what you have been using when you plot the Fourier transform in the continuous time case is you have been plotting magnitude versus frequency and phase versus frequency. There also the continuous time Fourier transform is a complex function of a real variable. There the real variable omega went from minus infinity to plus infinity. Okay. Now, if you look at this, so you have some original transform x of e to the j omega, and then when you shift this, it is getting multiplied by e to the minus j omega n naught. So, if you want to view this geometrically, what is happening here? So, what does this do? This is a complex number and it is being multiplied by e to the minus j omega n naught. So, what does it do in the complex plane? Phase modulation, not quite. Geometrically what is happening? Very good. It rotates, right. So, the geometric interpretation of multiplication of 2 complex numbers is the magnitudes get multiplied and the phase angles get added, right. In this case, if one of the complex numbers is e to the j omega, all it does is it cannot alter the magnitude, but merely rotate the complex number that it is multiplying, all right. So, now we can get a feel for what is happening here. So, let us now plot the Fourier transform. Sequence we are interested in is this. Later we will be looking at cos omega naught n. We will formally derive the Fourier transform of this, but in terms of equation this appears similar to what we had seen in continuous time. So, this is pi times delta omega minus omega naught plus delta omega plus omega naught, and sin omega naught n was pi by j delta omega minus omega naught minus delta omega plus omega naught. So, this looks frighteningly similar to its continuous time counterpart expression. The only difference of course here is, very good. So, in the continuous time case you had an impulse at plus omega naught and minus omega naught, and there you must have used the cap omega naught notation. You may have also used the little omega notation, but since here we want to compare and contrast CTFT and the DTFT, for the CTFT we will use the cap omega notation and little omega for the DTFT. But in the CTFT case you had only one impulse at plus omega naught and another impulse at minus omega naught. In the DTFT, because by definition it is periodic, when you write something like this, the periodicity is clearly not explicit. In fact, it is not periodic the way it is written. Therefore, what do you need to qualify this with to make sure that it is the DTFT? You have to specify the range over which this is valid. So, this is between this. Note that in the case like a to the n u of n, its DTFT is 1 by 1 minus a e to the minus j omega. All you needed to do there was you replace z by e to the j omega. Therefore, 1 by 1 minus a z inverse became 1 by 1 minus a e to the minus j omega. There you do not need to specify the range, because by the very nature of the expression, if you replace omega by omega plus 2 pi, the periodicity is there in the form that it is written. Okay. Now, coming back to this, so let us call this as the omega axis, and this is the real part and this is the imaginary part. Okay. Or rather, let me make this as the real part and this the imaginary part, and this is omega. Now, for cosine omega naught n, this is the DTFT. So, it has an impulse at omega naught and at minus omega naught. Therefore, at omega naught I have an impulse, at minus omega naught I have an impulse. Now, what I am going to do is I am going to take cosine, and remember this transform is purely real valued. So, that is why the transform lies completely in the real part plane. And now, when I take cosine and shift it, then I start to add phase, right. And remember, the geometric interpretation is a rotation, all right. And hence, when I rotate in this 3D plane, this impulse starts to rotate like this. So, now this comes like this. So, now this is rotated by an angle like this. This impulse starts to rotate in this direction, all right. So, if these are the two impulses, then when I start to shift, right? This rotates like this rotates like this, okay. And now I keep shifting, all right. I shift it enough so that cosine has now become sine. So now what will happen is this impulse will be like this impulse will be like this, all right. So the two impulses that were like this, they are now completely real. 90-degree shift, this will become like this will become like this. They are now completely lying in the imaginary plane, right. So that again you see from this expression. Therefore, the transform that you are used to seeing, so the transform is for cosine, you would have seen impulses like this, and for sine you would have seen impulses like this, correct. So this is nothing but the view of this 3D picture as viewed in this direction. After phase shifting enough so that it has become sine, the picture that you see here is nothing but this 3D picture viewed from the top. Now if you keep shifting further, this sine will become minus cosine. Therefore, what will happen is this keeps further rotating and the impulses will be completely pointing downwards. Again you shift further, minus cosine will become minus sine. Again you keep shifting further, minus sine will again will become cosine. So when you have shifted by enough samples so that cosine comes back to cosine, these two impulses would have rotated one complete rotation, all right. So this is the geometric picture associated with the shift, all right. So this kind of adds insight to the algebraic expressions. So any multiplication by a factor that is e to the minus j omega n naught merely twists the transform in the 3D complex plane, and clearly the magnitude does not change because it is mere rotation. Magnitude is related to the length does not change if you rotate, okay. X of n minus n naught was e to the minus j omega n naught x of e to the j omega, then extending this, somebody had this idea in mind, e to the minus j omega x of e to the j omega, and now instead of n naught the person used alpha, and now this became n minus alpha. So the point about this is it is not mere change of notation. Now alpha can be any quantity, not necessarily an integer, all right. So once you have this delay property, it suggests that you can delay a sequence by fractional amount. Now what is the interpretation of this? The interpretation of this is as follows. So we have a sequence like this. Associated with this sequence, an underlying envelope, continuous time signal. So, you can think of something like this. And because the underlying signal is continuous, suppose you take this and then delay the underlying continuous time envelope by some amount. Okay. Suppose you delay this by some amount. The point is, the underlying continuous time envelope can be delayed by any amount, not necessarily integer number of samples. Now, suppose you resample the shifted continuous time signal, but the point at which you sample remain the same. You sample exactly the same points. Therefore, now you will sample it here, 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 here and so on. You can think of now the new samples which are exactly at the same locations as the old, except now this in your mind you can think of this as taking the original underlying continuous time signal, shifting it by not necessarily an amount that is integer multiple of the sampling period. You are shifting it by say 2.5 samples and then you are resampling it. So, you will get the newly marked samples. So, you can interpret these new samples as taking the old ones and shifting it by fractional amount. So, this delay property helps you to bring in the notion of fractional shift, because e to the minus j omega n naught need not necessarily be an integer. So, what we will do is, yes. Yes, so the assumption is you have sampled it adequately so that the samples represent an underlying continuous time signal. So, that is the assumption that you are making. Through a discrete set of points, an arbitrary number of curves can pass through, but if you assume that the signal is band limited, which is what you have studied in sampling in signals and systems, it's a unique correspondence between samples and the underlying signal, continuous time signal. So, that is the assumption here. So, what we will do is, remember we had cos n pi by 5 and then we also looked at cos n pi by 5 minus pi by 2, and this was x of n minus 2.5. So, now what we will do is, we will take cos n pi by 5, apply this property and then obtain this signal by letting alpha to be minus 2.5, and we will do this in MATLAB. And the only thing that at this point you do not know is, right now omega is continuous, whereas on a computer implementation you have to implement it as samples. That is, the transform cannot exist on a continuum of values from 0 to 2 pi, it has to necessarily be sampled, and that we will come back to towards the last part of the course. So, only that step may not be clear to you. Other than that, all I am going to do is, I am going to implement this, and the transform again cannot be a continuum of values. So, transform also has to be machine implementable. This multiplication also has to be machine implementable. So, the connection between what is being done in MATLAB and the DTFT, this is exactly what I am going to implement. Okay. So, I have n points from 0 to 19. So, I have taken 20 samples and then this is my signal cos n pi by 5, and I am going to compute the transform. I need x of e to the j omega, that is obtained by this operation FFT of x. So, later we will talk about the DFT and we will talk about the FFT. So, this is the machine implementation of the DTFT. Okay. So, this is the transform. Okay. Now, I need to take the transform and multiply by e to the minus j 2.5 omega, all right. And remember, we will see symmetry properties later. Similar to the continuous time case, if the signal were real valued, the transform is symmetric in the CTFT. So, if you know the transforms from 0 to infinity, you know the transforms from 0 to minus infinity. Similarly, here if you know the transform from 0 to pi, you can recreate the transform from pi to 2 pi. So, that property we will also exploit. We will formally state that property later. I am using that in advance now. So, now I have this. So, this is what I am doing here. I have taken the first 11 samples. Remember, the sequence is 20 points, 0 to 19 contains 20 points. Later we will see that the transform also contains 20 points. I am only taking the first half. So, I am taking the transform from 1 to 11, that is, this is 0 to n by 2. N is 20, therefore n by 2 is 10. 0 to 10, MATLAB is 1 based index, therefore I am taking 1 to 11. And e to the minus j, here I have 2.5, and omega I have discretized. So, this is what the discretization of the omega is, 2 pi 0 1 2 up to 10 by 20. This corresponds to the discretization of the omega variable. Details will become clearer when we do the DFT and the FFT. So, I have now created e to the minus alpha omega times x of e to the j omega. This is what I have created in this step, but I have created this only from 0 to pi because I have taken only one half of the spectrum. Now, the second half of the spectrum is nothing but the complex conjugate of the first part and time reversed. Again, we will see this later. So, here the x1 vector that was created earlier is there as it is. X1 vector that was created before is there as it is. So, here what I have done is the flip up down time reverses the vector, you will see the need for time reversal later, and complex conjugation. Conjugate does the complex conjugate part, and I am taking the first half, I am complex conjugating it and time reversing it. But in the first part, I have the sample value at omega equal to 0 and at omega equal to pi. Those need not be repeated because they are common. Therefore, that is why I am taking only samples from 2 to n minus 1. Sample number 1 would correspond to omega equal to 0, which need not be repeated. Sample number n, which is the last vector, corresponds to pi again, which need not be repeated. So, this is the reason why I am taking only samples from 2 to n minus 1. Okay. And then I need to compute the inverse transform. Okay. So, the x1 vector that was created earlier, I am now doing the inverse transform. Earlier I had used FFT, that was the counterpart for the DTFT in terms of machine implementation. The inverse DTFT is accomplished by IFFT, and if things were ideal, because of the symmetry of the transform, the inverse transform would be real, but due to machine precision effects, the transform is not expected to be real, but the real part will have some very small machine epsilon values. To get rid of the small imaginary part, I am taking the real part. Okay. And now I need to plot. So, here what I have plotted is n from 0 to 19, and this is y. Y was obtained by taking cos n pi by 5, and then shifting it by 2.5 samples. So, if we have fractionally shifted the original sequence, and we are now comparing it with the ground truth. Ground truth is really cos n pi by 5 minus pi by 2. Remember, cos n pi by 5 minus pi by 2 is x of n minus 2.5, whatever that means. So, this is the ground truth, and y is taking cos n pi by 5 and shifting it in the frequency domain by applying a phase factor of 2.5. There you go. So, one curve is right on top of each other. So, the two curves here, one was y, which has been obtained by shifting by 2.5 samples of x. X was cos n pi by 5. I have shifted by 2.5 samples using this procedure, using the delay property. The other reference is really cos n pi by 5 minus pi by 2. Those lie right on top of each other. So, you can actually fractionally shift using the delay property.